I'll give an exposure on actually aircraft, what materials are used. If time permits, I'll give you the idea on what are the areas you can research. Okay, so my idea is not to teach any concepts. My idea is to just to give exposure, which I had learned in last 15 years, my career at aerospace sector, mainly in the DRDO. So I'll start with the funding schemes in the India. I'm sure NIT professors are well versed with what are the funding agencies in the country. But for the benefit of other stakeholders in the today's session, I just give a brief overview on what are the funding schemes in India, what are the funding bodies. Anusandhan National Research Foundation is the newly set up body, which is recently set up, and SCRB funding body is dissolved, which has been replaced by ANRF. Second is DST, and DRDO, ISRO, CSCR, Department of Atomic Energy. And if you have a partner from the industry, then you can apply the funding in Department of Scientific and Industrial Research. Assuming you wanted to use your science and technology to solve the social science engineering problems, then there is a funding agency called Indian Council of Social Science Research. Of course, all of you know about AICT since you are into the academics. And research grants, you can classify into two categories. The first one is basic research grants. I mean, which will fund you for your fundamental research, basic research, in addition to the applied research. And second is exclusively for the applied research grants, wherein output should be in the form of product or the process, or leads to some solution for the existing problem. And expected TRL levels, technology readiness levels, probably more than 3 in these funding modes. And in these funding modes, either they give you the trustee area or they give you the problem statement alone, standalone problem statements to solve it. Okay. So very briefly, if I tell you, ANRF has several funding. Some needs a multi-institutional, multidisciplinary collaborations. Some you need to do it as a standalone researcher, as a PI, even co-PI are not allowed. Co-PIs are not allowed. For instance, ARG, Advanced Research Grant, is the multidisciplinary, multi-institutional collaborative research program, wherein you're expected to collaborate with across the discipline. It's not like in a circuit and non-circuit branches engineering. It's engineering science with the social science, humanities, medical, agricultural kind of other domains. You have to collaborate, have a co-PI, and solve the problem statements. And the funding amount also in the order of crores, like about 5 crores for 5 years duration. And if you wish to be a researcher who wants to do the individual research, then Prime Minister Early Career Research Grant. And if you are from the socially underprivileged community, Inclusivity Research Grant, IRG, that is exclusively for the scheduled caste and scheduled tribe. To empower them, ANRS brought this scheme. And I think for NITs and IITs, they know about the Partnership Accelerated Research, Industrial Research Program. And suppose you are working on the problem statement and you need a funding for the travel and for some contingency, not for the executing the problem statement, just for as a supportive funding under the Matrix program, as long as your problem statement is in theoretical sciences or mathematical sciences or social sciences. And SERB has SURE and TAR scheme, which are going to get revamped shortly. And similarly, DST have SIST program, scheme for young scientists and technologists. This is the only scheme where even the master graduates can be a part of it as a PI or co-PI. And the AICT has research promotion schemes. Broadly, if you see ANRF fund, if you are an individual researcher, it funds up to 60 lakh rupees for 3 years duration project. Whereas if it is a problem statement which involves multi-institutional, multidisciplinary, you will be getting the grants in terms of crores, from 5 crores to 50 crores for the 5 years duration maximum period. So these are the fundings available for the basic as well as applied research. And if you have an inclination towards some streams or some domain or some trust area which are very specific, like for example, defense, space, or atomic energy. And there are funding modes, or social sciences, there are funding modes. DRDO has 4 panels: aeronautical panels, life sciences panel, armament panel, and naval research board. There are 4 research boards. In addition, you have extramural research and intellectual property rights. And for the startups, technology development fund. And recently, DRDO has set up DRDO Industry Academia, DIA, Industry Academia, cells at various IITs. In fact, NIT Jaipur also can pitch in for that DIA cells, since Jaipur doesn't have any other cell from the DRDO so far. IIT Delhi has currently, which is very close to you. And they also started giving funding to the academicians. And similarly, ISRO works in a different framework. Instead of giving trust area, they give only a problem statement, and they give clearly the key deliverables from the researchers or the collaborators or PIs, and which lab wants the problem to be solved and who is the domain scientist. All the information in the form of response basket. Every year, December 2nd week or 3rd week, they typically publish. So you're expected to provide the solutions and deliverables to the problem statements. DST has India with other countries bilateral calls, and the IRHPA kind of different calls are available, which is a collaborative work. Either India with other country researchers jointly work, or within the India multi-institutional collaborations. Like RRCAT Indur or BARC Bombay or IGIC or Kalpakam, they all come under Department of Atomic Energy. They do fund under BRNS program for the collaborative research in the field of atomic energy. As I said earlier, if you would like to pitch the problem statement which uses the science and technology to solve the social science problems, Indian Council of Social Science and Research, they also fund under the major and minor projects. There are some schemes exclusively for the women. I understand today programs, I don't think any women researchers are there. However, just for them, SCRB, DST, DSIR, they have a funding mode exclusively for the women, in which men are not eligible to even participate as a co-PA. And they also have a travel grants exclusively for under the wing schemes for the women researchers. And DST and UK jointly, they develop a woman to become a leader in the academic institution under the Women Leadership Program. So these are some scope for you to explore as a women researcher under the women category. And as a research scholars who are here wanted to have exposure at IIT and NIT and to taste the real good research ambience who are from the private institutions. For them, SCRB Karyashala, Ritika, IIT Delhi Summer Faculty Internship, INSA Visiting Scientist Program. These 4 programs are more relevant to you. And for other faculties who wanted to become a leader, IIT Jammu every year gives a leadership program under Ministry of Education. And recently, for the private college faculties who are suffering from the education recession, for example, like mechanical branches are having very low intake, for them, they have designed the program which are run by IITs and NITs, which is a PG certificate program offered by AICT. In case you opt that program and complete, it's a 6-month program, both online and offline. You're eligible to teach in the cross-disciplinary department if you have a PG certificate. This will help you in the calamity of education recession, which are currently faced in the EEE department, mechanical department, civil department, where the intake is typically low across the country. For those faculties, this will be a good opportunity. And some faculties are interested, rather than the research, wanted to become an entrepreneur through the startup. For them, DST Nidhi scheme, Prism scheme. These 2 schemes offer you the funding for startup. And there are some good postdocs and PhDs. Postdocs Inspire and Negru Science for CSIR labs. PhD Prime Minister Fellowship and US India Entrepreneurship Fund Fulbright Fellowships. So these are some important information which I thought I will share it to you. And lastly, if you want to organize any conference or seminar in your institution, or to go to abroad and present paper through government funding in international conference, there are some funding modes. AICT, I think all of you know. In addition to that, ANRF, they have ITG scheme. CSIR has travel grant scheme. DRDO in aerospace resource panel and ERIPR, under these two schemes, they offer you funding. And typically ISRO, ICMR, these are the domain specific. As long as your research is aligned to their domain, they do fund for your travel or to organize the event at your institutions. Okay. With this very brief, I'll start the today's session. Okay. This is a typical civil aircraft, civil helicopter. And these are the different parts in the aircraft. We call it those regions as the different names. Like for example, wing, fuselage, stabilizer, flight controls, landing gear. Or in the helicopter, you can see airframe, fuselage, pylon, stabilizer, tail boom. All of them are just a name to recognize us that this region corresponds to this name. But as a whole, if you see, these are 80 to 90% of them are made out of the same material, either lightweight alloy or carbon fiber reinforced plastic, except in the region where EMA shielding or EMA compatibility is required, where glass fiber reinforced plastic is used. Okay. Just to give a little exploded view to look at the intricacy of the fuselage, wing, or landing gear, there are so many parts. So if you, as an individual part, if you count in an airframe, there are about 1,000 plus. Similarly in the landing gear, similarly in the helicopter. And each has its own purpose, but essentially all of them are load-bearing structures. Okay. We will look at it one by one. So like ribs, stringers, spar, bulkhead, and so on. So a typical aircraft encounters variety of loading conditions, either mix of these loading conditions, or some may be very dominant. Tension, compression, torsion, shear, bending, or inherent loading in any part of the aircraft, plus fatigue loaded conditions. So just to give an idea, like when the aircraft take off or land, you can see at different region of the aircraft encounters different kind of loads or the forces. Like for example, compression force towards your fuselage, and wing encounters the torsional loads. And again, the fuselage, when it takes off, it encounters the bending load. In addition, when the aircraft moves at a different speed, especially in the military aircraft scenario, it encounters a very complex pattern of randomized fatigue loading. So just to give an idea, these are the essential parameters as a designer in the aircraft they will see before selecting the material. If I am a material designer or the aircraft designer, these properties we typically see. Why I mention these properties, when you research anything for the aircraft, you make sure that these property generations are taken care. For example, tension, compression, bending, torsion, impact, stiffness, high cycle fatigue. So we don't generally see the low cycle fatigue loading on the airframes. And fracture toughness and crack growth resistance. If it is a metal corrosion, if it is a polymer matrix composite, it's aging. And if I put two conductive material adjacent to each other in my assembly, I have to look at the galvanic corrosion compatibility. And typically, like Rajasthan, like your place, kind of a place is, if I operate my aircraft because of the sand and the high temperature, there is a possibility for the sand erosion on my airframe structure. So I have to look at the air erosion. Of course, there are many transmission components which has a contact, so leads to which are prone to the wear, so wear resistance. And my ultimate aim of any aircraft designer to reduce the weight of the aircraft, so lightweight. That is, I have to opt for the low density material. Just by saving a 1 kg, you can look at the kind of savings I get in the aircraft. In addition to the mission capability, if I look at in the military aircraft point of view, 1 kg of weight I reduce in the airframe structure or the engine, 1 kg of payload I can increase is in the form of weapon. Typically and conventionally, if you look at the material usage in the airframes, it starts with the wood, then the graduation from aluminum, then magnesium died down because of the corrosion issue. Then people have started thinking about using the titanium alloys, then the carbon fiber reinforced plastic. So these were the scenario maybe about 10 years ago. Even our Tejas aircraft has carbon fiber reinforced plastic in the airframe material. So we are self-reliant or sufficient in the CFRP stage. Now we are in a stage where we have started working on stealth materials, stealth composites. That is called radar absorbing materials. Okay. And our future mission, for example, advanced medium compact aircraft kind of AMCA projects, we are expecting to integrate the stealth composites in our airframe so that we will be in the club of stealth aircraft, which is a 5.5 generation aircraft. For the layman or for the novice in the field, aluminum alloy or the carbon fiber reinforced plastic, these are the two materials rules the airframe. Just to give an idea, in Boeing aircraft, so Boeing's older version to the present version, 747 to 787, you can see the amount of aluminum alloy usage has been drastically reduced, and the composites, that is mainly the CFRP usage has been increased from 747 to 787. You can see very clearly the pattern. Titanium, steel, they more or less stay same. In fact, steels are replaced with the titanium alloys, especially in the high strength regions. Earlier days, I use special steels, like for example, precipitation hardenable steel, maraging steel in some location where strength is the criteria. These regions are currently replaced with the titanium alloys. There are some beta titanium alloys which gives me the similar properties like steels. That's why in Boeing 870, 787, you can see the amount of titanium alloy usage has been increased from previous versions. People who are researching, they must understand in the aerospace sector or in the aluminum alloy sectors, these are the prominent alloys used in the aircraft. Take it in aircraft, civil or military. Aluminum copper alloy, that is 2014. Aluminum manganese alloy sheets for the floors are 6082 aluminum magnesium silicon alloy, or 7 series wherever I need a very high strength, 70510 instead of 7075 aluminum zinc alloy. These are the alloys are prominently used in the airframe structures. Okay. When I need a strength and toughness combination, I go for aluminum copper. When my focus is only the strength, I'll go for aluminum zinc. And when I need a very good formability, aluminum magnesium silicon. That's all is the logic to understand. These numbers, you must have a sense. You cannot have an aluminum alloy which have a strength more than 550 MPa. Okay. So if you're a serious researcher on aluminum alloy, how to increase this upper bound limit, that is 552. Let's say you come up with a novel combination of composition of the alloy or novel manufacturing like 3D printing, use it. Bring the strength to higher than 550 MPa, minimum 6% elongation. Okay, at least 7%, 6 to 7%. If you're able to achieve, that will get into the mainstream. That is the very good research you do. Otherwise, any research you do and you get me the property below this 550 MPa limit, or 6% below that limit, it's not useful for me at all in my airframe application or any aluminum alloy application, because I have a better material. Okay. Similarly, coming to the carbon fiber reinforced plastic, that is, we call it carbon epoxy prepreg, and glass epoxy prepreg. These are the two we use it. You can look at the density 1.6 to 1.9, even some are 1.3, and aluminum is 2.7 gram per cc. So you can understand the kind of a weight reduction I can get if I replace aluminum with CFRP. And you can also look at the strength. I can play with the strength. Very high strength I can get it. Okay, but only problem with this carbon fiber reinforced plastic is a high scatter of properties. Okay, and very complex manufacturing process. For a kind information, except HAL division, we don't have not even a single company in the country who can make the CFRP, that is a carbon fiber or glass fiber reinforced plastic, reliably to the aerospace quality requirements. That is the first thing. And we don't have in India, even including HAL or any, we don't have a raw material fabrication, mainly the carbon fibers or the glass fiber. Reliable carbon or glass fibers, we don't have a company to manufacture. So this is a potential area for the students or the faculty to look into the startup. Very high scope is there. And coming to the engine, which is completely contradictory to the airframe requirements. Engine operates at very high temperature, airframe operates at very low sub-zero temperature, because when you are at high altitude. So your components are exposed to very sub-zero temperature in airframe, whereas the components inside the engine are subjected to very high temperature in the aero engine. And just to give a very simple way of understanding, air is sucked, compressed in the compressor. Okay, this region is the compressor region. This is the fan region. Air is sucked by the fan. Then the compression takes place in the compressor. Then it will go to the combustion chamber where the fuel is added. Then combustion takes place. Then part of the air through the bypass duct, it will go off. Part of the air will get into this compressor and getting compressed, and it go to the turbine, which will do the useful, work. So this is a simple explanation for this jet engine. This is the turbo shaft engine, mainly for the helicopters, where the power is my priority rather than the speed. Okay, but the mechanism is same like your jet engine. Take the air, compress it, and combustion takes place in the combustion chamber, and which will be used to do the useful work through the turbine. And the turbine taps the energy and send it to your rotors for the rotations. Okay. So that's a simple explanation. But if you look at it, the kind of the operating conditions or an environment a typical aero engine experiences, you can see that usually the low cycle fatigue, which is contrary to the airframe where the high cycle fatigue, high centrifugal force, and the vibration loads leads to the fatigue as a major failure mode at higher temperature in the air engines. That is, the thermal fatigue is the major failure mode in most of the aero engine components. And when you suck the air, there are possibility for the foreign object, like for example, any bird or something hit happens on the front page, part of the engine, it leads to the big danger. So you need to have high impact strength of the front region, that are fan regions. Then the high thermal load, because everything happens at very high temperature. I'll show you in the next slide what is the kind of a temperature a typical engine experiences inside the aero engine, different regions. Then engine sucks the air, which are from the dry region or wet regions or the marine regions. So all leads to the hot corrosion and the oxidation environment, or hot salt corrosion, hot erosion environment for the aero engine components. So these are the properties. As a aero engine designer, I look at it from the material perspective. So when you are working on the material which are used in the jet engine or turbo shaft engine or turbo propeller engine, or even for the space engines, please make sure that these properties are designed, are tested, and data are generated, which will be useful for the designer. Low cycle fatigue, high cycle fatigue, fracture toughness, thermal fatigue. Instead of creep, stress rupture properties. Of course, your basic strength and torsional properties are needed mainly for the simulation. And oxidation, hot corrosion, hot erosion, and most importantly, density should be as low as possible so that the total weight of the engine is reduced. What are the materials used in the engine? So in the front portion of the fan regions, typically you find aluminum alloys or the polymer matrix composites where the temperature are in the order of less than 100 degrees Celsius. Entire compressor regions are ruled by titanium alloys. So there are two regions or three regions in the aircraft where titanium alloys are used. One is a compressor portion of the aero engine. Second is landing gear region. Third is wherever I have a high strength steel usage where I can reach the beta titanium alloys. And similar to the titanium alloys, super alloys are used only in the combustion chamber and turbine sections like turbine blade, discs, and other components. And among that super alloys, nickel and cobalt are widely used. Based alloys or super alloys are used. Wherever I have a gear kind of a transmission system parts, I use either low alloy steel, nickel, chromium, molybdenum, or PH steels, precipitation hardenable steels. So high strength low alloy steels or the high alloy steels are used. So these are the composition of the alloy used, cluster of the alloys used in the aero engine. And you can see the percentage of the each alloy usage. So engine is ruled by nickel-based superalloy and titanium alloys, which constitute about 70 to 75%. Just to give an idea on a cross section of the aero engine, the red color regions are high temperature prone regions where either titanium or superalloys are used. And just to give an idea, aluminum alloys are used in application where the temperature exposure is less than 120 degrees Celsius. I cannot use aluminum alloy in a scenario where temperature exceeds 120 degrees. Similarly, these all are designer rules and how the designers select the materials. And any regions which are experiencing temperature less than 300, then steels. Any regions which are experiencing temperature in the order of 450 to 500 or lesser than that, titanium alloys fits. Titanium alloys fit into the bill. Any regions which experiences the temperature more than 500 degree, you are left with the choice of super alloys. And whatever you are researching in last 10 years or 20 years, like intermetallics or high entropy alloys, ceramic matrix composites, or powder metallurgy based dispersion strengthened alloy, none of them are there in any of the aircraft or any of the space parts in the even in the global, for your kind of information. Okay, none of them have been implemented. One or two are in the experimental stage, but none of them are in any production scale or the presently flying aircrafts. So this is what I understood by studying all the aircrafts across the world, across the countries who are running the different flights. What I understand, our in Indian projects also, since I have exposure from all the projects, what I understand, everything high entropy alloy to intermetallics to aluminum matrix composites or magnesium matrix composites, whatever you research, none of them has gone into the real system so far. Okay, the main reason is property scattering, process is consistency. These are the problems. So these are not those problems are not still solved. And as the research in the academic region, academic sphere, whatever happens, all are in laboratory scales and simple geometry. When I put the geometry as one more constraint into your process, the process consistency is affected significantly. Second is, when you have a geometry, the property what it has to, it guaranteed in a simple geometry or a simple coupon, I no longer get in the complex geometry. So the factor of geometry is ignored in the research. That leads to the adoption of this alloy into the mainstream, delayed. Just to give an idea, in a typical aero engine, look at the left side is your air intake in the front part of the engine. The right side exhaust. You can just reel your imagination and understand how the pressure from the 1 atmosphere, when I suck the air, when it reaches the combustion chamber after the compression, it will be 10 atmosphere. So you can understand what kind of a heavy loads are faced by the compressor section of the aircraft, fan and compressor sections. And then, at the same pressure, it exits to the turbine regions from the combustion chamber. Then it gets, used by the turbine to generate the energy or for the propulsions. So all the parts inside the aero engine experiences the high pressure than the normal ambient pressure. Second is a look at the temperature. Up to compression, somewhere around 400, 500 degrees Celsius. When it gets into the combustion chamber, the very high temperature, somewhere in the order of 1300, only thermal load, now no mechanical forces there. But when it gets into the turbine, both mechanical and the thermal load, very high temperature with the very high loading conditions. That's why you use the single crystal blades, cooling channel, thermal barrier coating, all these combinations you bring into the turbine regions, but we don't use it in the compressor regions or the combustion chamber, those things. So you can look at the temperatures, and similarly the speed, air speed starts with, let's say, 1500 meter per second, when it exits somewhere around 500 meter per second. Okay, just to give a feel about how the engine works, a typical aero engine works, you get an idea about it. So B stands for Boeing, A stands for Airbus. So you can understand the titanium usage since 1962 so far to 2020. So titanium alloys usage has been significantly increased from somewhere around 1% to now currently about 20% in a typical aero engine. Okay, which titanium alloys or what grades of titanium alloys are used in a typical aircraft or the aero engine? Titanium 6 aluminum 4 vanadium, that is alpha beta titanium alloy, is a single workhorse. 95% of the titanium alloy usage in the aero engine are this alloy. Okay, and if I wanted to use it in the sheet form, extra low interstitial Ti64. And other alloy categories, for example, titanium 6242 or 6222. Okay, these are replacement for Ti64 in a region where strength requirement is higher, temperature is slightly lower, somewhere around 400 degrees Celsius. And there is only one alloy which is a beta titanium alloy used in the aerospace or the aero engine is titanium 10 vanadium 2 iron 3 aluminum. 1023 we call it. Very famous alloy. In fact, in India, 5 years ago, we have implemented this alloy in one of our project. This is the first alloy replaces high strength steels in airframe structures. And beautiful alloy, but the research in this alloy are very, very limited. Most of the people work on Ti64. And you can look at this kind of a strength it offers, 1100 to 1200 MPa. Okay, and with the very good elastic modulus, most importantly, the fracture toughness. And titanium 15333 is in research phase. This is also a promising alloy in the field of high strength titanium alloys. Titanium 3 aluminum 2.5 vanadium is used in the tubes application, titanium tubes application in the aircraft. Only these alloys you find in the typical aircraft. And when you go to the Russian aircraft, Russian aero engines, the logic of titanium alloy design remains same, but the grade names may differ and the composition is slightly tweaked, and which you don't find in the Western aero engines. Similarly, in the field of steels, you don't find any plain garment steels or the cast irons, kind of a conventional steels or the cast irons used in the automobile in the aircraft. You only find low alloy steels of nickel chromium molybdenum or chromium molybdenum or molybdenum steel. Wherever you need a carburizings or the nitriding, like a case car racing or nitriding kind of the low alloy steels are used, transmission systems. And wherever I need a very high strength, because among the commercial alloy, managing steel is the stands top because it offers you the strength of about 1700 to 2000 MPa. That is 2 GPa, you get it as a strength. You can tweak it based on the grades and the heat treatment. So used in the landing gear, mainly in the naval applications. And wherever I have a sheets where I need a chemical resistance, corrosion resistance, I go for the 316L. Wherever I need the strength with the corrosion resistance, the 15 pi 5 precipitation hardenable stainless steel is used. And very rarely we use spring steels in the application where the springs are used in the aircraft. Only these steels are used in the aircrafts, either in the aero engine or the transmission system or the landing gear. Super alloys, coming to the super alloys. So wasp alloy, Inconel 719 are the rulers in a moderate temperature regions. For example, the third stage of turbines and other regions. Stability of Inconel 718 is somewhere around 650 degrees Celsius. Wasp alloy is somewhere around 700 to 750 degrees Celsius. If I want very high temperature, then you have to go for the cobalt-based superalloy or the nickel-based superalloy, Nimonic series, where the iron is not present. And turbines where the very high temperature on the order of 1000, 1100, people go for directional solidified alloys, super alloys like MAR M247, which I have mentioned here. And if you want to go for a single crystal, which is much better than this MAR M247, which is CM2SX10. For your kind information, the single crystal technology is the very complex technology available only with Russians and Americans. Okay, and we have got the transfer of technology, so we know how to make that super alloy single crystal blades in the country through the Russian technology. Okay, and which is very complex technology. And we are in a stage where we don't have indigenous technology for the CMSX, reliable technology for the single crystal. So let's look at it just a little more elaborative or a descriptive way. The left side is equiaxed grain structure, then the directionally solidified, then the single crystal. This is the evolution of turbine blades, which are experiencing very high temperature with a very high load, somewhere around 1000 to 1200 degrees Celsius. So moment I eliminate the grain boundary, make it align in one direction, my creep strength or the stress rupture property improves. When I totally eliminate the grain boundary, so there is no possibility of the weakest region in my turbine blades, which gives me much higher high temperature property, especially creep or the stress rupture properties. Let's say I put a cooling channel inside to minimize the thermal concentration or the thermal gradient. I can push the temperature limit to the further. This is one innovation happened in the field of turbine blades technology. The next is like a jacket. When we have a winter, how we put the jacket to protect ourselves. Similarly, I put the ceramic coatings, thermal barrier coating. Yttrium stabilized zirconia. That's the only TBC used in the across the world in the turbine blades. Okay. Now the rare earth oxides are experimented in that field. So if I put the coverage on it, I'll be getting this further, thermal protections, or I can push my temperature a little higher, turbine inlet temperature higher, so that my engine efficiency increases. So now we are in a stage where we have a thermal barrier coating, we have a cooling channel, we have a single crystal all together with the support from the Russia. Okay, but still as the indigenous technology, we are still evolving. We don't have a technology, so that is one area where you can research. Taking further 2-3 minutes to close it. What are the manufacturing technology we use to fabricate the parts for the typical aircraft and or aero engine? Sand casting, forging, machining, extrusion, powder metallurgy, autoclave technology, in welding, we use the electron beam or the laser or TIG welding. And recent adoption to the field of manufacturing in the aerospace sector is additive manufacturing, mainly the metal additive manufacturing. We don't use any polymer additive manufacturing because there are no polymer parts, standalone polymer parts in the aircraft. Just to give an idea, when I have very massive parts with a very complex geometry like a helicopter gearbox or the aircraft gearbox, I opt sand casting. When I have big parts, not a complex geometry, but which needs a strength, mainly the fatigue prone properties or the fatigue properties, like a disc or the landing gear, I go for the forging. If I'm unable to do the forging, I go for the extrusion or the rolling, kind of a forming operation to get my shape. Let's say I'm unable, I have a material which are having the composition diverse in nature, like a metal matrix composites. I typically use powder metallurgy. Powder metallurgy is used only in two applications in the entire aero sector. One is fasteners, another one is the brake pad. And recently people are exploring PM-based powder metallurgy processed turbine disc, but still in the exploration stage, but I have not seen any application in any of the aircraft so far. If I am unable to make through the casting route or the forming route or the powder metallurgy, I opt for machining, where the structure is so complex, I cannot make it through any of the conventional manufacturing process. I opt for this kind of a machining technology to get the shape. For example, impeller or the instrument panel, or I have a parts of 5 or 6 which needs to be assembled. I use machining followed by welding. Okay. Brazing is used only in the turbine regions, turbine blade regions, where we need to braze certain regions, mainly the cooling channel regions, where I use the brazing. These are the list of tests I do for qualification of any aircraft parts. I want just you to take the snapshot, because when you develop this kind of data on the material, which will be useful for us. Again, it's application specific. Not all the tests are done on all the parts. Depending on the application, if it's a fasteners, I emphasize on shear. If it is a airframe parts which are exposed to fatigue loading, then it's high cycle fatigue. Same fatigue loading experience in the aero engine, then low cycle fatigue. Likewise, so we have to strategically decide so that I don't overperform or overdo or over waste the testing. And another area which is least explored in by the metallurgists or mechanical engineers are identification of the defects. How properties are important to decide the importance for the performance decision. Similarly, defects also. If it is a surface defects, we use fluorescent penetrant. If it is a ferromagnetic material like nickel, cobalt, or iron, for the surface and subsurface, we use magnetic particle inspection. If it is the internal defects, which are three-dimensional in nature, we use X-ray radiography. If it is the internal defects, which are two-dimensional in nature, like a crack, three-dimension means porosity, crack, then I use the ultrasound test. These are the logics. There are specification, AMS, aerospace material specification. And with the interest of time, I think I must close at this point. Maybe in the next session, when I get a time, when I get a platform, I'll explain you what are the advancement we should explore as a researcher to contribute into the field. With this, I just wanted to close my presentation, and I thank Professor for a wonderful opportunity to share my thoughts. I run a broadcast group where I share informations related to the research schemes, anything for the academic related activities like awards, fellowships, research grants, anything related to that. I usually share to the people who are in my contact. Anyone would like to join, send their name and department. I'll save their name and I'll add in my broadcast. This I do as a selfless service for the academic community, because I believe you guys will be the important asset for the country who will be setting up next generation for the India's growth. So with that intent, I'm doing. Any messages I sent to you may be useful to you, may be useful to someone else. So please forward to others if it is not useful to you. With this, I thank once again the professors from NITs Jaipur, and any questions I'll be happy to answer.
Thank you, sir. Thank you, sir. Thank you very much. From last 1 year, I am continuously getting every update. Where are you going for any expert lecture in any NIT or any laboratory or any company? And sometimes it is very much useful to us also. So we come to know about the what type of research is going on in different institutions and laboratories. So it is a very good platform which we have been headed by you, and
Thank you, sir.
was a very nice interaction with the students and faculty members. So we are very much thankful, and in the future also we will expect from you that you will always be cooperate with us, and we will
Sure, sir.
definitely
Sure.
engage ourselves with you in some research project also. Already we had a meeting with you, and we are
Yeah.
working upon your guidance, which you have given us some input, and soon we will be coming with some proposal with you that will be definitely be advised by you, sir. So any
Sure, sir.
questions from the audience is welcome.
You
Participant
can
may
text
write
also
in
as
the
a
chat
message.
box. Yes, sir.
You can also text. I can answer those questions.
Sir, I think there is no question from the participants. So thank you, sir. Thank you very
Thank you,
much.
sir. Thank you.
Thank you, sir.
Thank you, sir.
Thanks a lot.
Thank you, sir.
Guys, within 10 minutes, we will start the another session. Next speaker is from IIT Bombay, Professor Asim Tiwari sir. We will start within 10 minutes.